Hi everyone. So in the previous video, we have seen the DC and AC analysis of our MOSFET amplifier. So we saw that when we are analyzing our MOSFET amplifier, we can break it into two parts, DC analysis and AC analysis. When we are doing the DC analysis, we will not consider any AC sources. And when we are doing the AC analysis, we will not consider any DC sources. That's it. So that we are going to write. So now we are going to study small signal model, but before that I will tell you what we need to do. So when you are doing the AC analysis, what you will do? You will nullify all the DC sources. What do you mean by nullifying? If you have studied the network analysis, what do you mean by nullifying? Nullifying means your voltage source will be replaced with the short circuit. Voltage source will be replaced with short circuit. So voltage source is shorted. Better I should use this line. So by this you will understand, right? Voltage source will be short circuited, and what about current source? Current source will be open circuited. Nullifying means zero. So if voltage is zero, that means short circuit. If current is zero, that means open circuit, right? So voltage source will be short circuited, and if current is zero, that means open circuited. This is current, it will be open circuited, right? And generally the coupling capacitor will be shorted. Generally this happens, the coupling capacitor gets shorted and parasitic capacitors are open circuited. We will study about it when we study the frequency response. We will study about it deeply. So generally coupling capacitors, if you see any capacitor in the circuit, that will be shorted while doing the AC analysis. While doing the AC analysis, the capacitor will be shorted generally, but when it will not be shorted or when it will be open circuited, that we will see when we study frequency response. So for now you have to consider that whenever you see a capacitor, while doing the AC analysis you will open circuit it. Sorry, while doing the AC analysis you will short circuit it. So coupling capacitor will be shorted. So simply a capacitor will be replaced by a short circuit. This is the capacitor. This will be replaced by short circuit. Well and good. And while doing the DC analysis, what you will do? You will nullify all the AC sources. We have seen here when we do the DC analysis, what we do? We nullify all the AC sources. So voltage source is shorted. Here voltage source is shorted. AC voltage source is shorted. That means it is zero. So only VGG is left. And in this one, DC voltage source is shorted. That means this VGG is zero. So only AC source is there. That's it. This is what you need to do. While doing the DC analysis, AC voltage source will be shorted. While doing the AC analysis, DC voltage source will be shorted. And while doing the DC analysis, what you will do? While doing the DC analysis, coupling capacitor will be open circuited. The capacitors will be open circuited, not short circuited. It will be open circuited. The coupling capacitors will be open circuited. These are the capacitors. So they will be open circuited, not short circuited. Open circuited. So this coupling capacitor is shown by CC. CC. Here this will be shorted, it will be open circuited. Well and good. Let's see the small signal model now. So what we are seeing the small signal model. Small signal model. So we will see three kind of models, and then I will tell you what kind of model we are going to use. So three kind of model we will see one by one. So this is an NMOS. Listen to me very carefully. What we are seeing? Small signal model. That means we are going to consider only small signal. Now we are studying small signal model. So we are going to consider only small signal. So I am assuming I have applied a small VGS. I am assuming I have applied a small VGS across gate to source. This is my small signal voltage, small signal input, small signal voltage. I can say small signal voltage. We are doing the small signal analysis. Even this VDS will also be a small signal. Although I will not write it, but if you are doing the small signal analysis, every signal present in the circuit will be small signal. Your current will also be small signal. Your voltage will also be small signal. So if you apply a small signal voltage, what is the current that flows? Tell me. What is the current that flows? If you apply a small signal VGS voltage, what is the AC current? Here we have seen the magnitude. That was GM-VGS. That's it. This is you need to remember. This is what you need to remember. Very, very important. If you apply a small signal VGS voltage, what is the current that flows? GM-VGS. That's it. So if you apply a small signal VGS voltage, there will be a current, that is GM-VGS. So this is what we are going to show. If you apply a small signal voltage between gate to source, there will be a GM-VGS current flowing from drain to source. If you apply a small signal voltage VGS between gate to source, there will be a current flowing GM-VGS that will be from drain to source. Say yes or no. And this current will certainly be 0, because I have told you gate current is always 0 ampere. So this is what we need to show, and this is how we show it. I am applying a voltage from gate to source. This is my gate, this is my source. I am applying a small signal voltage, that is VGS. My current flows from drain to source. This is my drain, and since I have shorted them, so this will be source only. So current flows from drain to source, that is GM-VGS. Now go to the first page of our MOS physics. Now we have connected it. Go to the first page of our MOS physics. What did we want? We wanted a dependent current source, and this is what we have got. If you apply a VGS, you are getting GM-VGS. That's it. This is what we wanted. Say yes or no, right? Yeah. Screen lag नहीं करना ना. I don't think screen is lagging. Is it lagging? Not lagging. Yeah. Okay. So GM-VGS current we are getting. One thing we are forgetting. What is that? Output resistance. We should not forget output resistance. R naught. Our op-amp is working, not our op-amp, our MOSFET is working in saturation region. In saturation region, there is a R naught. If lambda is not equal to 0. So that R naught we should not forget. So R naught also I will put here. Just a second. This is the R naught. Here lambda is not equal to 0. If lambda is 0, this R naught will be infinity. Why we are putting this R naught? Because our MOSFET is working in saturation region. If it was working in linear region, we would have put a capital R on. The value is different. What is the value of this small R naught? If you remember, never forget this value. This is very important. What is the value of this small R naught? That is 1 upon lambda ID set, but ideal one. 1 upon lambda ID set, but ideal one. That's it. This is the value of this R naught. Well and good. So this is what we are saying. This is the first model, which is known as pi model, and we are not going to use this one. This is generally used by a lot of aspirants, but once you see the big circuit, this will create complexity. So we are not going to use this one. So which one we are going to use? T model. No, we are not going to use T model as well, but we will see it because that is important. So what do we see in T model? Here I am drawing drain. So one thing I know, that from drain GM-VGS current is flowing, that I know. So I can say that from drain GM-VGS current is flowing. From drain to it is going towards source. So but I know this thing that from drain GM-VGS current is flowing. GM-VGS current is flowing. Let's assume I call this one as gate. From gate there is no current, I know one thing. And let's assume this is my source. This is my source. So let's connect this. So tell me one thing. This is my small VGS voltage, right? Between gate to source. This is my small VGS voltage. And I know one thing, that is here GM-VGS current is flowing. Here GM-VGS current is flowing. I have applied VGS voltage and I know the current GM-VGS. What will be the resistance here then? The resistance will be 1 by GM. And the current in the complete path, this is the complete current, that is GM-VGS. The complete current flowing is GM-VGS. And one thing we cannot forget, that is between drain to source we will have an output resistance. Between drain to source we will have an output resistance. इसको थोड़ा छोटा करना पड़ेगा एरो को, हो जा भाई। ओके, दूसरा ही ड्रॉ कर देते हैं। सो दिस वाज द करंट GM VGS, and between drain to source we are having a resistance which is R naught. This we cannot ignore. So what did you understand here? That drain, gate and source, I have VGS. Between gate to source I have VGS potential, and I know there will be GM VGS current flowing. So what will be the resistance? That would be 1 by GM, because voltage upon resistance is the current, So current is GM VGS. Voltage upon resistance is the current, so the resistance would be 1 by GM. And from drain I know GM VGS current is flowing. That's it. This is what I did. And between drain to source I have a resistance R naught. So this is the second method. We are also not going to use this one. So what we are going to use? We are smart. We are not going to draw any model. We are never going to draw any model in the examination, even in the interview. So what we will do in the interview or in the examination? The MOS will be there. So I will keep MOS as it is. Here there is gate. There is this source. I know there will be some potential here. Whatever the potential is there, the potential is VGS. Whatever the potential is there, we are going to make a current GM VGS like this. Because we know whatever the potential is there between gate to source, the current flowing would be GM VGS from up to down. That's it. And one R naught resistance we will connect. That we will remember. And we will also remember one thing. What is that? That this current is 0. This current is 0 ampere. We will see gate to source. We know if VGS potential is applied, GM VGS current will be flowing. Between drain to source, I have R naught resistance. That's it. No model, nothing like that. There will be big circuits. Nothing will happen. I know one thing. If I am having VGS potential, GM VGS current will be flowing and R naught resistance will be there. Tell me one thing. If gate and source are shorted, then what will happen to the MOS? If gate and source are shorted, somehow gate and source are shorted, then what will happen in the MOS? Tell me. MOS will be open circuited. Why so? Because VGS will be 0. If gate and source are shorted, then VGS will be 0. If VGS is 0, that means current is 0. So this GM VGS current will be 0. So only R naught will be left. Only R naught will be left. So this complete MOS will be open circuited. Are you getting this point? So like that we are going to analyze. We are not going to draw these kind of complex circuits. We are not going to draw anything. We will just remember, okay, this potential, current, GM VGS, that's it. And R naught resistance at the outside. Same thing we are going to do for PMOS. So what do you do for PMOS? Between source to gate you are having a source will be the common one. Source will be the common one. So here source is at higher potential and gate is at lower potential. So VSG potential we will have. Whatever VSG potential you are having, whatever, this is source, this is gate. So whatever VSG potential are having, based on that potential, between source to drain you will be having a current. Between source to drain you will be having a current. That is GMVSG. GMVSG. Look, from where the arrow is getting out now, that is at higher potential. Or wherever the arrow is, that will be at lower potential. Here where the arrow is at gate, so that will be at lower potential. Here where the arrow is, this is at source. So source is at lower potential. That's it. So GMVGS in case of PMOS and GMVSG in case of GMVGS in case of NMOS and GMVSG in case of PMOS. source to gate, GM VSG, this potential. So current will be from source to drain. The current will be from source to drain. And the resistance is R0. Between source and drain, the resistance will be R0. That's it. What will be the second model? Here I have the VSG potential. That means if I have the VSG potential, that means here the resistance will be 1 by GM. This is source. So here I am having VSG potential. This is gate. Let's assume this is gate. This is gate. So here I will be having 1 by GM potential. This is gate. The current I know is 0 ampere. Why the resistance is 1 by GM? Because I am having VSG potential here. And from source to drain I am having GM VSG current. Now some people may get it out. Some people may get it out. Sir, why are you not drawing 1 by GM resistance here? Why not that? Think about it. Why I am not drawing 1 by GM resistance here? Sir, you can say, sir, 1 by GM resistance can be here as well because GM VSG current is flowing. Why did I make this 1 by GM resistance here? Because I am having VSG potential here. Here you are not having VSG potential. You can't say this potential is VSG. No, this potential is VGD. So if you are having VSG potential, then only you can draw 1 by GM resistance. Here you know one thing that in gate, here you know one thing that is in gate GM VSG current is flowing. That's it. This is what you know. Nothing else you know. You don't know any potential or anything. Are you getting this point? And why it is GM capital VSG? It is small VSG. Are you getting this point? GM VSG current is flowing. Now you can't say, sir, I will get to know some potential here, GM VGD. If I know the potential, then I can draw some resistance here. But the current is depending on VSG, not VGD. If the current was depending on VGD, you could have drawn the resistance. If the current here, this current would have been GM VGD. If this current would have been GM VGD, then you would have drawn 1 by GM resistance here and GM VGD current source here. Are you getting this point? If the current was GM VGD, then across VGD potential 1 by GM resistance would have been there. And from source, GM VGD current source would have been there. But here we only know the VSG potential. And the current is depending on VSG potential. So my current is GM VSG. So VGD potential has nothing to do. So you can't make it as a resistance. So some people may have a doubt. Although whenever teacher explain this model, they don't give this much of logic. They directly make, okay, 1 by GM will be there, GM VSG is there. But here now you have understood all the complete logic, why we are making a resistance, why we are making a current source. Well and good. And between source to drain, I will be having a resistance R0. But is that the model we are going to use? No, because we are smart enough. What we are going to use? We are simply going to use the given MOS circuit only. Look, if you are studying for the first time, it may seem like very much difficult or anything. Okay, how will I remember all these things? But once you solve the problems, you will be habitual. You will be very much habitual with all these things. Like this is gate. By the arrow sign only you will write, okay, this will be source. So from source to gate, okay, so there will be this current GM VSG. That's it. And this is the potential VSG. And this is R0. This is R0. This is drain. That's it. This is what we are going to use. I know one thing, based on the potential applied, I can write down the current, and if the current I know, then there is a resistance R0 connected to that. That's it. Understood? Well and good. So these are the two models which is very important. Based on these models only, your complete next chapters are based. So this is the most difficult part of MOSFET amplifier as per the student. We will make it very, very easy that within seconds you will be able to answer a lot of big circuits, right? So yeah, let's move on to the next. Like we are going to solve the questions now, but before that I want to give you a concept of port impedance. Like if you haven't studied the network analysis, then it will be used. If you have studied the network analysis, you already know what is Thevenin resistance. What is Thevenin resistance? Considering all other sources shorted, we find the resistance at a particular node. That is Thevenin resistance, and this is what we are going to do in the port impedance. Like they will give you a circuit, like in the examination, what you will see, like this circuit will be given, and they will ask you what will be the resistance from this side. They can ask you these kind of questions. What will be the resistance from this side? So how will you find those? So what you will do, you will first put all the independent sources to 0. That means you will nullify all the independent sources. Current source will be open circuited, voltage source will be shorted. That's it. Current source open circuited, voltage source shorted. Then you will apply Vx here. Let's assume I was supposed to find resistance at this side. So apply Vx here and get Ix out of it. My resistance would be Rx by Vx. That's it. Did you get it? Let's assume in this question I was asked to find Rx here. So what I will do, I will put all the independent sources to 0. Then I will apply Vx here and get Ix out of it. So my Rx would be Vx by Ix. That's it. Understood? So these kind of questions will be asked. Let's understand it with an example. It will be more clear to you. They are asking you Rx from here. What will be the Rx? What will be the Thevenin resistance? Rx port impedance is same as the Thevenin resistance only. So what will be the Thevenin resistance? R1 parallel R2. But let's solve it with that method. So what we are going to do, this will be shorted. All the independent sources will be shorted. I should not put it as Vx. V is fine. So all the independent sources will be shorted. So this will be shorted. So R1 will come in parallel to R2. R1 is parallel to R2. Now you are asked to find the resistance from here. Here you can directly see it is R1 parallel R2, or what you can do, you can apply Vx potential. And get Ix out of it. So Vx by R2 plus Vx by R1 is equals to Ix. So Vx by Ix, which is Rx, is equals to R1 parallel with R2. That's it. Right? Now in this question they are asking you Rx from here. What you will do? You will apply Vx here and get Ix out of it. Okay, let's make it more interesting. Let's make this question more interesting. This question was given to you and you were asked to find Rx from here. Now people will have a doubt, sir. What we will do? First we will short circuit this V. If the V is shorted, then what we will do? What did I tell you? What is the first step? Make all the independent sources equals to 0. The V should be shorted. Then what was the second step? That apply Vx and Ix. Wherever it was asked to find, apply Vx and Ix. If this is shorted, then how do I apply Vx and Ix? So yeah, this is the thing. Like if you are finding the resistance at the input side, you have to consider the Vx source input only. The Vx source that you are going to apply, that will be the input only. Because if input is shorted, if input is gone, then how will you apply any voltage source here? Did you understand this point? So if I short circuit this, I am not able to apply any input source. So this is the input source only. This I can make as Vx. So this will be my Vx, and from here I will be getting Ix out of it. Or just think that simply forget this. There was no voltage source, nothing was there. If you are asked to find at the input side only, forget about Forget about any other source. There was no source. Just apply Vx and Ix. That's it. Or just consider the input as a source only. Input as the applied source only. You are going to apply Vx and Ix. You consider the input as the applied source only. Got my point? So Vx and Ix is flowing out of it. R1, R2. So Rx would be, what will be Rx? Vx by Ix, that is R1 plus R2 only. That's it. Right? R1 plus R2. Let's come to this question now. Now these kind of questions are considered to be tough as per the gate aspirant. They think, okay, what kind of amplifier it is? Do I remember the expression? Nothing, no need to remember anything. We know simple concept. What we are asked to find? We are asked to find the resistance from here. What we will do? Short circuit the independent sources. Vin is the independent source. I will short circuit it. So if I short circuit it, what I will get? This is shorted. And VDD will also be shorted. VDD will also be shorted, right? No sources are there. VDD is the DC supply, okay? VDD is the DC supply. And you needed to find Rx from this terminal. So what you will do? You will apply a Vx here and get Ix out of it. You apply a Vx here, get Ix out of it. Now people will have one doubt. Sir, you have short circuited the gate. Now the transistor will not even turn on. This is the doubt people may have. But you don't need to think about it. Don't need to think about it. Why so? Because you have applied this Vx. You have applied this Vx. This potential is 0, this potential is Vx. So what is your VGS now? VGS is minus Vx. VGS is gate to source is minus Vx. So what was the current? GM VGS in this direction. This was the current. The current that was supposed to flow was GM VGS. And VGS is minus Vx. So what will be the current? Current will be flowing upward. The current will be flowing upward. That would be GM Vx. Did you understand this point? Now people will say, sir, how the current can flow from source to drain? It cannot flow. In an NMOS, how the current can flow from source to drain? It cannot flow. I know that. It cannot flow from source to drain. But this is the small signal analysis. Here I should have written small signal resistance. Small signal resistance. Small signal resistance. Find the small signal resistance. This we are doing the small signal analysis. In the MOSFET, there are VDD, there are VGG as well. Here also VGG is also given. So this is just the analysis. It's not that VGG is gone. VGG is there, but for the analysis purpose we are doing this. Are you getting this point? They asked us to find the small signal resistance. In the Vin, you are having VGG as well, even the AC signal as well. What was the AC signal? Vn sin omega t. Both you are having. But for the analysis purpose, what did you do? You short circuit them. But now it's not that if you short circuit them, the transistor will be in cutoff. No, the transistor will be there as it is. But for the analysis purpose, we are doing. So you don't need to think that transistor will be in cutoff now. No, the transistor will not be cut off. You are doing the small signal analysis now. What you need to think only? You just need to think that there will be GM VGS current here and R0 will be there, which I have already drawn. That's it. This is all you need to think. VDD is shorted, Vin is shorted. So what will the current? Current will be GMVX, upper side. Did you understand this point? The current was supposed to flow GMVGS like this, GMVGS, GMVGS. But what is happening? VG is 0 and source is at Vx potential. So the current is in the downward direction, the current is minus GMVx. So in the upward direction, current would be GMVx. That's it. So the current is flowing GMVx in the upward direction. And this current flow is flowing like this. Now you can apply nodal analysis here. Nodal analysis at this point. So I am applying nodal at Vx. Nodal at Vx. So Vx by R naught, this current Vx by R naught, upper side, Vx by R naught. This current is upper side Vx by R naught plus Gm Vx is equals to Ix. Are you guys agreeing to this point? Vx by R naught, Vx by R naught plus Gm Vx is equals to Ix. Say yes or no. Now tell me one thing. People can think that, some people can think that, sir, this GMVX current will be flowing through this R naught. So why cannot you say GMVX is equal to minus Vx by R naught? Are you guys having this doubt? If you are having this doubt, what I will say, forget it. You should not have this doubt. Why so? Because this current will not be equal, because here there is ground. So even the ground can eat up some current. What is the current ground is eating up? That is GMVX plus Vx by R naught. The ground is eating up this much current. So there is ground. Okay, if this ground was not there, then the current would have been the same. But there is ground mentioned. So the ground can eat up the current. So how much current the ground is eating up? That is GMVX plus Vx by R naught. So do not have these kind of doubts. But I have seen some people having these kind of doubts. So that's why I am taking all the doubts here. Right, since the course is recorded. So if you are having the doubt, you can comment down. Certainly I will answer, or you can ask in the Telegram group by screenshot or anything, or you can note down. We can have the session. So we can certainly answer all the doubts, but here I am addressing all the common doubts which I have already faced from the students. Right. So yeah, GMVX current, Vx by R naught current is equals to Ix. So what is the resistance you get? 1 plus Gm R naught by R naught is equals to Ix. Is equals to Ix. So Vx by Ix, that means Rx we are getting R naught upon 1 plus Gm R naught. R naught upon 1 plus Gm R naught. Right? Okay. This is the Rx we are getting. Now tell me one more thing. First let's remove this. If this was the scene, that R1 was here, R2 was here, and I was applying Vx here and I was getting Ix out of it. So what did I write? Vx by R1. I knew one thing, answer would be R1 parallel R2. Here the answer would be R1 parallel R2. I can directly see. But what did I write? Vx by R1 plus Vx by R2 is equals to Ix. So my answer was this resistance parallel with this resistance. R1 parallel with this R1 parallel R2. If I am writing Vx by R0 plus Vx by 1 upon Gm is equals to Ix. Isn't it the same? Vx by R0 plus Vx by 1 upon Gm is equals to Ix. So what will be my resistance? R0 parallel with 1 by Gm. Say yes or no. Right? So you can call this resistance as R0 parallel 1 by Gm. So the resistance that you have wrote, that would be R0 parallel 1 by Gm. So the other answer would be Rx, that would be 1 by Gm parallel R0. That's it. This is the answer. First thing we got to know, sir, gate is short there. That means the current will not be 0. Why the current will not be 0? Because we are doing the analysis, we are doing the AC analysis, we are doing the small signal analysis. It's not that we have eradicated the VDD, we have eradicated the VSS or VGG. We are just doing the analysis for the analysis purpose. Like we have to find the resistance. They are there only. But if they are asking the small signal resistance, this is how we need to do it. So Ix, Gm Vx, Vx by R0 current, right? And Ix current is flowing there. So Vx by R0 plus Gm, Vx by R0 plus Gm Vx is equals to Ix. So Vx by Ix is R0 parallel with 1 by Gm. Now you will remember it for the rest of the time. How will you remember it? So if in the NMOS, if you see from downward, if you see this arrow, if you see this arrow will be replaced by 1 by Gm. This is grounded, here this is grounded, this arrow will be replaced by 1 by Gm. So 1 by Gm parallel to R0, that's it. What I mean to say, if this is the scene, what you need to remember, let me write it down. Whatever that you need to remember, here I will write. If this is a scene and they are asking you, what do you see from here? What do you see from here? You are doing the small signal analysis, what do you see from here? You see from here, that is 1 by Gm, that's it. If they are asking from the arrow side, you are seeing 1 by Gm, that's it. The resistance will be 1 by Gm. So this is what you need to remember. You can remember this small thing, right? Because again and again it will be used again and again in your analysis, that you need to see from downward, you see 1 by Gm. The condition is this should be shorted. That is the condition. This should be shorted. The complete analysis I have given here, and if this is also shorted, so from here you see 1 by Gm parallel with R0, right? So let's not write it here. So what do you see? What you will say, sir? I will say from source to ground I see 1 by Gm. What do you say? From source to ground I see 1 by Gm. That's it. From source to ground I see 1 by Gm. This is what you will say. From source to ground I see 1 by Gm. Right? From here 1 by Gm, or you can simply derive it as well, because if you are applying Vs potential here, what will be the current flowing upward? That would be Gm Vx. So Gm Vx is equals to Ix. So what is your Vx by Ix? That is 1 by Gm. But the condition is this gate should be grounded. Then only you can see 1 by Gm, right? Or in the small signal model as well, here in this small signal model, from here we are asking. So what is that? 1 by Gm only, right? So only the basic thing that you need to remember, that is from source to ground you are seeing 1 by Gm. Say yes or no. Agreed? Very good. Now find the resistance from looking from this terminal. Small signal resistance. Again, this is small signal resistance. This you need to answer on your own. What do you think? What will be the answer? This is PMOS. This is not NMOS. This is PMOS. So what will be the answer? 1 by Gm parallel with R0 only. Why so? Because what will be the condition now? This will be the condition that this will be shorted. This will be shorted. This is also grounded. This is R0. What you need to do? You need to apply a Vx and get Ix current out of it. So this is Vx. This Vx will also go here. The potential is, what is the current downward? The current downward is Gm Vsg. The current downward is Gm Vsg. From here to here, potential is from here to here. Here what is the potential? From here to here, right? The side at which the arrow is given, which is at lower, that is at lower potential. So Gm Vgs and here Gm Vsg. So the current was Gm Vsg. So Gm Vs is at potential Vx and gate is at 0. So what will be the current? Gm Vx. So the current flowing downward is Gm Vx. The current flowing downward is Gm Vx, right? And what is the current flowing here? This potential is also Vx. The current flowing downward is Vx by R0. So Gm Vx plus Vx by R0 is equals to Ix. Tell me what will be the answer? Rx will be 1 by Gm parallel R0. This is the same circuit, same as PMOS. Nothing different is there. Same as NMOS, sorry. This is the same circuit only, but here you feel like something different is there. This is the same circuit only. So here what did you understand? That if an PMOS is given and they are asking you for a resistance. A PMOS is given and they are asking you for a resistance from here. So what do you see? You will say from source to ground I see 1 by Gm. That's it. From source to ground I see 1 by Gm. And if there is parallel R0, then that will also be included. From source to ground I see 1 by Gm. That's it. Here from source to ground I see 1 by Gm, and then R0 is also there parallel with R0. Here what do you see? From source to ground I see 1 by Gm parallel with R0. If you remember only this much of thing, your problem will reduce to very small part. Otherwise you will have to make very complex circuit. Just from source you need to see the resistance. From source you always see 1 by Gm. That's it. The condition is gate should be grounded. From source to ground you always see 1 by Gm. That's it. From source to ground you always see 1 by Gm. Well and good. Let's move on to the next question. So I know I have not teach you common source amplifier, common gate amplifier, common drain amplifier. Nothing has been taught. But only by using the concept that we have studied till now, we can analyze any kind of amplifier. So this kind of circuit is given. Here there is RS, R0, 3 volt, minus 3 volt, Vs is given, V0 is given. So Vs is the small signal source. The DC supply are plus 3 and minus 3. R0 is also there, W by L given, Vt is given, mu and C. You have to find the R0 value such that quiescent drain voltage is 0. Quiescent drain voltage. What do you mean by quiescent drain voltage? That is known as actually Q point, or you can say DC. Whenever quiescent is given, that means they are talking about DC. Quiescent drain voltage is 0. So DC drain voltage should be 0. So only you are going to consider DC source. Vs is the small signal source. There is no VGG applied. There is no VGG. In case of input, what we were applying previously, we were applying Vin. Vin was our VGG plus small signal voltage. But here there is no VGG. But will the transistor turn on? Yeah, it will turn on. Why so? Because minus 3 is there. So your capital VGS would be 3 volt. Gate is at 0 potential, but source is at minus 3. So first you need to find the DC drain voltage. So first we will do DC analysis. So in DC analysis, I will not consider any AC source. I will only consider DC source. So DC source is 3 volt. That is connected to R0. R0 is simply an element. So nothing it has to do with DC or AC. Then I have the resist. I have this, which is minus 3 volt. This was our V0. And here I was having RS. And Vs is 0. Small signal, because this is small signal source. That means it will be AC. If they are writing small signal source, they need not to mention AC. You have to consider by your own that it will be AC only. It's not necessary that they will write it is going to be AC. You have to consider by your own that this is AC only. So consider this is AC only. So this is shorted. Right? What is the current here? 0 ampere. The current in the RS resistance is 0 ampere. So there is no meaning of this RS, because RS will have 0 voltage drop. Right? RS will have 0 voltage drop. So there is no meaning of RS. You can remove the RS. Now what will be the current here? That will be capital ID, or you can write IDC. Capital IDC. What that current will be? Capital IDC would be. Here one thing should also be written, or is that necessary to be written? No, that is not necessary to be written, because they are asking the drain voltage should be 0. If drain voltage is 0, that means this potential is 0. Then what will be your VDS? This potential is 0. So VDS will be 3 volt. What will be your VGS? VGS will also be 3 volt only, because this potential is 0. Here you can see, or okay, on next page I should write. What is your target? What is your target? Target is your V0 should be 0 volt. So if V0 is 0 volt, then what will be your VDS? What will be your VDS? 3 volt only. What will be your VGS? This is gate which is at 0, source is at minus 3. VGS is 3 volt. What is VT? VT is 1 volt. So what is V over drive? That is 2 volt. So here VDS is greater than V overdrive. That means this is in saturation region. So you will apply the saturation region current equation only. So that will be mu n. Have you forgot the equation? No, we should not forget the equation. VGS minus VT whole square. So what is the value of mu n CXW by L? That is 100 micro by 2. VGS, what is the value of VGS? 0 minus 3, 3 minus 1 whole square, that is IDC. So IDC you get is 4 4 200 micro ampere. This is the IDC we are getting. Your target is to make the V naught equals to 0. So what is your V naught? V naught is equals to 3 minus IDC into R naught, and that should be equals to 0. So IDC into R naught should be equals to 3. So R naught should be equals to 3 by IDC, which is 200 micro. From here R naught will be equals to what? This will be 10 to the power minus 4. So 10 to the power 4 will go up. 35, 15 kilo ohm. R naught will be 15 kilo ohm. Say yes or no. Did you understand this point? Did you understand this question? So in the first question they asked us to make the DC drain voltage equals to 0. Coefficient drain voltage equals to 0. So we have to do the DC analysis. They have mentioned that Vs is the small signal AC source. So Vs is gone. 3 volt and minus 3 volt will remain there. So RS will have 0 current. So 0 voltage drop. There is no meaning of RS. So forget about RS as well. Our target is to make V naught equals to 0. So V naught is 0, then our MOS is in saturation region. Then we found out the current was 200 microampere. We needed to make VDS equals to 0, 3 minus IDC into R naught equals to 0. Now people will say, sir, it will have some AC component as well. Yeah, it will have AC component, but they are talking about DC only. So we have done that DC analysis only. In the next question, they are asking small signal voltage gain. They have mentioned small signal voltage gain. Small signal, that means small signal means AC. Whenever you find small signal, they are asking AC. So now we are going to do the AC analysis. So in the AC analysis, we will not consider any DC source. AC analysis. We are going to do the AC analysis. So this 3 volt will be grounded. 3 volt is gone. Then you are having the R naught here, which we have already found 15 kilo. Then you are having this MOS. Then you will be having Vs here. Okay, I will make it like this. Vs Rs. Now since Rs is having 0 ampere current, so this particular node will be Vs only, right? And this 3 volt minus 3 volt will also be grounded. Here it was 3 volt, here it was minus 3 volt, both are grounded. And this is your V naught. You need to find V naught by Vs. This is you need to find, right? This is what you need to find. This potential is Vs only. Well and good. So what will be the current here? Tell me. The current will be Gm VGS. What is the value of VGS? Small signal analysis we are doing. What is the value of VGS? That is Vs only. Vs, this potential. You are finding VGS. What is the potential of VG? Gate voltage, that is Vs. What is the potential of source potential? That is 0. So Gm Vs current is flowing. Now this Gm Vs current is flowing here as well. The same Gm Vs current is flowing here as well. So what will be the value of V naught? V naught, this I am calling, this was R naught only, no? This was R naught, right? This was R naught. So what will be the value of V naught? That will be minus Gm Vs into R naught. Current into resistance, that's it. Minus Gm Vs into R naught. So your V naught by Vs is, since this is 0, this will be negative, right? Current is flowing, current always flow from high to low potential. So this V naught is low potential. So V naught by Vs. Current always flow from high to low potential, but in a resistance. I need to make the statement clear. The statement that current flows from high to low potential, that is wrong. I hope you have studied this in network analysis. Since we are discussing this just as small topic, like if this is 5 volt, this is 5 ohm resistance, what is the current flowing? 1 ampere, right? Now people say the current flows from high to low resistance, sorry, high to low potential. What is the potential difference here between these 2 points? 0 volt. What is the current flowing? 1 ampere. Even if there is 0 volt potential difference, current is flowing, that is 1 ampere. The current flows from high to low potential in a resistance, in an element, right? Yeah. So this was not a matter of concern, just I explained a small point. So V naught by Vs is our minus Gm R naught. This is our answer, but we know the value of R naught. R naught we have, but Gm value we don't have. How we will find? What is the formula of Gm? Gm is a DC parameter. What is the formula of Gm? The formula of Gm is mu n Cox W by L V capital Gs minus Vt. Here you cannot do the mistake of writing small vgs. It is capital Vgs because Gm is a DC parameter. I did not even talk about small signal model when we were studying Gm, right? I told you even during the derivation. Let's see the derivation. Let's get back to the lecture and see the derivation. So when we derived it here, what we replaced with Gm? What we replaced? We replaced this one as Gm, right? IDC is a DC parameter, VGG is a DC parameter, VT is a DC parameter. Complete Gm is a DC parameter. Although it is used in AC analysis, but it is a DC parameter. So while finding the Gm value, you have to do the DC analysis. So for finding the Gm value, you have to do the DC analysis. Are you getting this point? But on the previous page only, we have done the DC analysis. So from there, we can pick the values. So what is the value of mu n Cox W by L? That is 100 micro. What is the value of VGS minus VT? VGS was 3 volt. Because we have to pick the values from DC analysis because Gm is a DC parameter and Vt is 1. Vt is 1. So Gm would be 200 micro mho. 200 micro mho. Because Gm is the opposite of resistance, transconductance it is. Opposite of resistance. So Gm is 200 micro mho. So here we can put the values now. Minus 200 micro is 10 to the power minus 6 into 1.5 into 10 to the power 4, right? This would make V naught by Vs equals to minus 3. R naught is 15 kilo ohm actually, 15 kilo ohm. So I put 1.5 into 10 to the power 4 because this will be 10 to the power minus 4. This will be cancelled. 1.5 into 2 will be minus 3. Minus 3 volt per volt. This is the gain. That's it. Say yes or no. Did you understand this complete question? Without even studying common drain, common gate, those terms, nothing you have seen, but still you are able to answer the amplifier question, which will not be which a lot of gate epsilon cannot answer, or even in the interview or in the written test. Just the circuit was given. They have made the biasing like this. We studied different kind of biasing, but any engineer, any designer can make his own biasing. So this is the biasing he has used. Is that biasing correct? Yeah, this is correct because we have seen here, we saw here that it is perfectly working in saturation region. The current is also coming. He wanted to make drain voltage to be 0. So R naught is 15 kilo ohm. If he had said that I want my drain voltage to be minus 2, I want my drain voltage to be minus 2, then what will be VDS? If he wanted drain voltage to be minus 2, then what would have been your VDS value? That would be 1 volt. And if it was 1 volt, then it would not go into saturation, it would go into linear region, then it would not work as an amplifier. Are you getting this point? But he has made the question smartly. He has made the question smartly, making sure that V naught is 0, so that your VDS is higher than V overdrive voltage. Then everything is matched. Then if the transistor is working in saturation region, we know the model. We know the model that now we are going to do the AC analysis. Vs is there, Vs current is flowing. So V naught will be simply GM Vs into R naught, that's it. V naught by Vs is minus GM R naught. Now R naught value is we are having, but we are not having the value of GM. GM is a DC parameter, we know, mu n CXW by L, Vgs minus Vt, 200 micro we got, right? You can find the value of GM by some other formulas as well. There were 3 formulas. What were the formulas? Let's revise it once again, then we will end the lecture. What was the formulas of GM? One formula we have already used. What was the other one? These are very, very important, so always remember it. 2 into mu n CXW by L ID. Everything is under the root. 2 into mu n CXW by L ID under root. This was the one formula. And let's use it for finding the value. So that would be 2 into, what is mu n CXW by L? That is 100 micro. And what is ID? ID we have already found. That came out to be 200 micro. 200 micro. So micro will come out. That would be micro only. This would make 100. And this is 2. So GM is 200 micro only, no? Yeah, 200 micro mho. So if you solve this, you get 200 micro mho. Well and good. Or what was the other formula? The other formula was 2IDC by VGS minus VT. DC current 2 into, what is the DC current? That is 200 micro. DC current was 200. What is VGS minus VT? That is 2. So GM is 200 micro mho. So anytime you need to use any formula, by all the formulas you will get the same answer. But even in some question, you will have only the value of ID and VGS minus VT. Then what you will do? You will apply this formula for GM. In the some question you will have only these 2 values, then you will apply this formula. And in some question you are having all the values, so you can apply any formula. So collectively it will be used. So I hope you are understanding the lecture. I hope you are enjoying the MOS physics. Not MOS physics, now we are moving to amplifier. So I hope you are enjoying the MOSFETs, and just keep on studying along with. Otherwise you will be forgetting everything. Just keep on studying, and I will give you n number of questions in MOSFET amplifier, n number of questions. A lot of questions will be there, and you will be able to answer within seconds. Once you are done with the complete course, you will be able to answer within seconds. So just keep on studying, right? Okay, thank you. Let's meet in the next lecture. In the next lecture, we are going to study common source amplifier. Okay.